In the original paper, transformer, they said like, okay, I have this block, very simple block, just linear layers, getting one sequence, process it into another sequence, right? And what I want to do, I want to get one maybe, I mean, the original application they were looking to was translation. I have one sentence in one language, right? I want to process the sequence into a sequence of numbers and then give that sequence of numbers to my decoder to generate a new sequence in another language, right? And of course, when I do self-attention, I'm going to get the first sequence, right? That is probably better than the very original input sequence, right? But since I'm doing just linear process, it's probably not enough to do it once, right? How can I handle that then? How can I improve my process? You add a nonlinearity, of course, and what you do next? More layers, right? You just go deep, right? Like any other architecture we know. We process one set of sequences, right? This sequence, I just process it into another, and then I treat this new sequence, attention sequence, again as an input sequence, and process it with self-attention once again, right? Hopefully, the next one is going to be even better, right? And if I keep doing it for enough number of times, then I'm going to get one sequence of numbers, which is perfect for my decoder, right? My decoder just looks at it and says, well, this is the output, right? So what they get as the idea, they say like, okay, I have the input sequence X, I process it to A1, right? Then I treat A1 as a kind of another input sequence. A1 hopefully is just capturing the temporal connections or temporal correlations much better as compared to input X, right? And then you get A1 as the input to a new attention layer, and then you compute A2, right? And you keep on going like this. You do it for n, for example, different layers. Then the very output is again a sequence of numbers. That one hopefully has processed the whole temporal connections very, very efficiently. Now, just as a kind of dummy intuitive example, to have a bit of understanding what is happening, maybe you want to find out, like, as I said, semantic analysis. You want to find out, this is a sentence, what is it about, right? Then, if you are processing it sequentially in time, you're going to get the first word, right, in the sentence, and this is not about science, so you go for the next one, and so on. Oh, this is about science, right? You're going to maybe copy it by gating or something inside your memory, right? And you keep on going, right? And then somewhere in between, it's going to get mixed with the other words as well, right? At the very end, you're going to have one memory, that is the hidden state, which is capturing many things which are about science, right? And then hopefully, these are things that are dominating everything else inside the sentence, and you are able to say this is about science, right? But if you have words which are about science and are about sport, both of them, right? They're going to get a bit complicated, right, for the neural network to capture that. Unless the neural network really understands that, well, the ball that is coming here, right, is talking about the ball I just throw from the roof, right? I'm talking about gravity. I'm not talking about football, right? It should understand that. How does it understand when it gets to the word ball, right? It's going to just attend to everybody else, right? And then what is happening here is somehow taking you up one layer, and in the next layer, that ball is changing to something, right? Ball/science, not ball/sport, right? And now when you give it into your decoder starts to see that, well, there was a ball inside the sentence, but it was not the ball used in the sport, right? This is the one used for examining the gravity, right? And then, still it's about science. You see it? So this is a sort of process that you do in depth. You're just, it's like you're, by attending to other tokens, you're somehow, writing indices, writing descriptions on every single token, right? And then this is giving more information, more context for your decoder to decode it. So the thing that you do, you get your sequence, you process it, you get your first sequence. Again, you pass it through the next layer, and next layer towards the very, very end. Everybody's clear? Questions? No question? Okay, so obviously these layers going to have their own weights. The weights is independent, obviously, because you want to increase the capacity of your model. And then this is a kind of deep processing of the sequence without sequential connections anymore, right? Now, when people started to write it down, they said like, well, this guy sounds like a convolution. Why? Because what did we do in convolution? We get one image, right? And we look at one part of it, right? We get the same weights, right? We go for another part. We get the same weights. We go for the next part and so on, right? And then we get one new map. That new map is having a bunch of features, right? And then we again say, okay, let's treat this as another image. It's a kind of imaginary image, which we do not understand, but neural network understands, right? And then the neural network is again looking at this processed image, treated the same way, right? You're going to say, look at the first part, same weights, we go for the next part, same weights, next part, and so on, right? And you keep on processing up to some point where you have this very output feature that is perfectly somehow capturing all the context inside the image, right? You're going to have a bunch of values on top corner indicating that there are very sharp edges inside the image, right? There are some other values somewhere else inside the feature which is indicating that there are multiple objects inside the image and so on, right? So that was the whole process happening inside the convolution. And this is roughly the same thing, right? So they have, in attention, we have, for example, fixed weights to compute the values, keys, and queries, right? We also go through the entries of the sequence using the same weights, right? So here, when I want to process this guy, these weights are including the weights for keys, queries, and values, right? And I use the same weights to compute values and queries and keys for every single value, right? So I use same weights, fix them, and then go over everybody in the sequence, right? And the last thing is that when I compute the output, I compute the output from the very last sequence, which is hopefully capturing the temporal connections, right? And same thing we used to do with convolution, right? In convolution, we get the same weight. The filter was the same in each layer, right? And that filter, you use it to process the whole image, right? So the feature of every single patch of pixels was computed with exactly the same weights, right? And also the output, you just process your first image. You gradually start to get spatial connections between the pixels. And at the very output, you start to compute your output from last set of features, which somehow capture the spatial connections, spatial correlations completely in your input image, right? Now, one thing that we did in the convolution was that we started with a very rich image, right? And we processed it step by step, right? But what did we do in terms of dimensions? What did we do with that tensor? We start, for example, with an RGB image, 3 channels, very rich, like, say, 1,000 times 1,000 pixel, right? But what we do when we compute next layers? We decrease the size. Then what we do instead to just keep the information there? Increase the number of channels, right? So we do not do one convolution per layer, right? We do multiple convolutions per layer, right? And every convolution is just taking the same image, computing a set of features in a separate channel, right? And we gradually increase the number of channels and reduce the size of every channel, right? Then we would say, okay, the information of everybody is somehow captured in one of the channels, right? Every aspect, right? Okay, maybe we can do the same thing here, right? Why should I get one sequence and do one self-attention on it, right? It's just one unit, right? I just copy this unit again with different weights and process it as well, right? I'm going to have 2 outputs at the same time, right? 2 output sequences. And then I treat those 2 output sequences at 2 channels, right? I can do it as much as I want, right? This was the idea of doing it multi-head, right? So basically, each head of self-attention is one layer of self-attention, which is running in parallel on the same sequence, right? So the idea was something like this. So you have multiple heads of attention, right? Each of these boxes that you see here is exactly the self-attention we had, right? But they have their own weights. All right, it's cool? So this sequence is going to go inside one head, right? And then at the output, it's going to give the attention sequence for that head. So the first head, I'm showing it by W1. These are the weights inside the first head. And the corresponding sequence is A1. You see the superscript 1 here, right, in brackets. That is the output of the first head, right? A1, 1, A1, 2, and so on. A1T, right? The first head gives me one sequence, right? If I get another head with different weights, it's going to give me another sequence, right? And I'm going to do it by H heads, right? H different heads. Every single head gives me one sequence. Then what do I do? Once I computed everybody here, then I'm going to treat the concatenated version in time as one giant attention output. Everybody's clear? So x1 to xt go inside the complete multi-head attention. Then you're going to compute at every single head, you're going to compute every single time one attention. Then all the attention one time are going to concatenate together, and then it gives you the first time attention. Everybody's clear? You got the idea? So multi-head attention is basically attention, just you do it with multiple layers, right? So what is the direct benefit of doing this? Any idea? Yes. You can do it, but if you do it with a giant self-attention, with a lot of weights, it still works, right? It adds parallel computation, right? It makes it more parallel, right? You can compute every single output of the head could be very small, right? And then all of them together could be large, right? I could do it with a larger self-attention, right? There are some other things inside, like, for example, if I add a nonlinear layer here, right? So it's going to change the value of the computation, and it could potentially help, right? But this is not the only thing. The key point here is that if I have a very giant self-attention with the weights, like the values that I generate are very large, right? Then I can just process the whole sequence with that one single layer, right? Yeah, but this way I am adding more parallel computations because every single part of my vector is computed independently, right? Yes.
Wouldn't that take the same amount of time?
I mean, if you really implement every layer completely in parallel, then yes. But you're not doing that, right? At the end of the day, every processor is capable of doing one self-attention with limited size, right? And then if you want to have a giant size at the output, you can do it. So this is one of the key reasons that you do this multi-head. But the other point is that, well, from convolution, as I told you, we have this idea. If we increase the number of channels, probably every channel is going to separately focus in one aspect of the input, right? Same thing could happen here. Everybody's clear? Questions? Now, one minor thing. Say I have the input, so x that I'm putting as the input, say x is of dimension n, okay? Right now. Now, say every single attention that I compute here is of dimension d0. You see? Every single attention at time for every single head. Okay? This is d0. What is the size of the complete attention vector at every single time? H d0, right? Head times the size of every single attention, right? H, number of heads, times that. Now, h d0, the thing that we usually do is that we design this d0 in a way that h d0, this size, the size of the concatenated attention at every single time, is exactly the size of x. Okay? This is a practical, something that we do usually in practice. Every single x. Every single x. I'm going to show it here. So if x is of size n, right? So you're going to set d0 and h in a way that d times h times d0 is going to be n, right? Everybody's clear? So you do it usually this way. So you usually choose d0 to be n divided by the number of heads, right? And then what you can say when I increase the number of heads, the length of every single attention I compute is going to decrease. This is a typical practice. It's not a mandatory thing, but this is usually the case because the embedding size, like x's, are embeddings of the tokens, right? And usually we have somehow designed the embedding size efficiently, like the size we have chosen is fine enough to represent a language. If you are thinking about language processing, then probably you don't want to increase the size, right? You don't want to reduce the size as well because you don't want to lose tokens, right? But you don't need to increase it as well. So you keep it the same size. The only thing is that when you increase the heads, you're going to reduce the size of every single layer, right? Yes?
If they're not like integer multiples,
Typically they are. They are powers of 2. Yeah, but if it is not, of course, 1 or 2 is not important, right?
but you have to make it the same size. You have to like 0 size, or
You can do that. If you don't do it, nothing going to harm. I mean, you can still process that vector if you just fit every dimension correctly. But this is a common practice. Like n is 512 or 1024, and then h is, I don't know, 16, 32, and then it's going to match always, right? Yes? Each head generates, right. Right. Just use your weight matrix that way, right? So you generate every single h by multiplying the corresponding weight wh with x, right? And then that weight should be d0 times n, right? The size of the matrix. Which one is d0? d0 is one of these guys, right? This guy is d0, right? Every single of them is d0. So say d0 is 5, right? And you have 10 heads, right? So you have 10 different vectors. Each of them is of size 5, right? And then all together are of size 50, right? When you concatenate them. Right? Right, but that attention has nothing to do with the values. Attentions are computed from values, right? You're talking about this one, right? D0 is size of this guy, right? And these are scalars, right? So you have x1 to xt, say capital T, this capital T is 10, right? And then say size of this guy is 4, h, right? So every single time you have a vector of size 4, right? This is the value vector. Now, you get the keys and queries, you compute alphas, right? Alphas are scalars, right? So at time t, you would say there is one alpha for myself, there is one alpha for the neighbors, and so on, right? Every corresponding alpha is getting multiplied to the h vector at that time, and then you add them up, right? At the end of the time, this weighted sum is going to be of the same size as h, 4, right? So the thing coming out here is 4, right? And it has nothing to do with the time length, right? It's just the embedding size of h, correct? Now, the thing that you are doing here, than in the multi-head version. So every single of these guys that you see is of size 4, right? If I have 5 of them, say I have 5 different heads, right? And every single guy is 4, then I append them. I concatenate them, right? And all of things together is of size 20, right? And what I said was that these x's are usually also in size 20, right? So you usually divide things in a way that x goes in, every single token is a vector of size 20, and then after concatenation, after you put all of them together, you again end up with a size 20 every single time, right? Is it clear? Questions? No question? Okay. Yeah. Now, one key reason that we keep the dimension the same, as I told you, you usually do that because the embedding size is fine enough. There's no reason to add more or less. But one key reason is that we also use a lot of skip connection when we build transformers. Like you go deep in depth, then you add skip connections as well, because they are going to help, gradients passing, right? And since we're doing that, we would be happy to have all the outputs same size as the input, so that if at some point we want to add the input of another layer to this one, we can easily do that, right? But as I told you, this is not a kind of mandatory thing, right? You can always do a linear transform and match the dimensions, right? Okay, that's it. One question, is it okay that I keep on going, because I need to finish it on Friday, right? And we have the last chapter left, so at least I make sure like this one is over, right? Okay, thanks. So yeah, so as I said, self-attention captures the temporal correlation, and yeah, there were a bunch of practical things that they just faced when they were implementing it in the original paper. One of the things that they noted was that, well, the features that they are extracting are not complex enough. They simply said that maybe we can just add a nonlinear layer as well, right? When we compute the attention, maybe we can activate it again, right? By doing that, we are like, I get this attention. After getting this one, before I go for the next layer, I just do one activation. And if you do that, this is nonlinearity, and we do know that adding nonlinearity would help, right? So they just added this one also in the architecture. The main reason was to just make the architecture more complex, because it was obvious they're just doing linear computations, right? And linear computation for a long sequence doesn't sound like something sophisticated, right? But they just wanted to make it as complex as possible to just be able to capture more context, okay? So now, doing this, they ended up having this particular unit, and this is the unit that nowadays is known as the self-attention unit. When they usually say multi-head self-attention, they simply mean this complete unit, right? What it does, it gets your sequence, it passes through multiple heads. Concatenated, you have a sequence of attentions, right? You again activate them, right? And then you're going to get your output. This is one layer of self-attention, right? If you want to do enough processing, you're going to just add them in a row, right? So one layer, you get your first sequence. You again pass it through the next layer. You get your next sequence, and so on, right? Yes?
Since we have softmax in initial attention,
Right.
we still add a nonlinear.
This, as I said, this is mostly practical point. I mean, your point is correct. I mean, since we have softmax inside this, connecting it directly to the next layer, it does not reduce the whole thing into one layer. But from deep neural networks, they had the feeling if we add nonlinearity, it's going to help more, right? So they just simply add it. I mean, if you simply add ReLU, I mean, you can always reduce it to a linear connection, right? But you typically use the nonlinear one. Questions? No question. Okay, and yeah, so this complete self-attention layer is going to get one sequence in time, and it's going to give you another sequence. The new sequence is less meaningful for you as a human being, but more meaningful to the neural network as a kind of machine working with those numbers, right? And that is a better thing as compared to the original one, maybe if you want to just capture the temporal connections. And a deep self-attention architecture is basically you get this guy and you just repeat it as much as you want to just get very deep, and you finally get your output, right? Yeah, so the guys in the original paper, they just came up with this idea, they implemented this, they saw that, well, this is working very well. If you want to just do a basic sentiment analysis, this is doing perfect. They didn't expect this, but it was working, and somehow it made sense later on because those time connections were doing not too much things as compared to the attention. And when you do a very rich set of attention layers, then probably you don't need those time connections. So they were just disturbing the backpropagation. They were doing nothing, right? Now, one question that you might have is that can't we use this idea of self-attention to build another encoder-decoder architecture, exactly like what we did with RNNs? This means that I start with my tokens in German, right? I give it to one self-attention layer, I get another sequence of numbers, right? I again do self-attention, I get another sequence, and I keep on going, right? Maybe I do it for 10 layers, 20 layers, and then finally I have one sequence, same length, of a bunch of numbers, right? Then I get this one and give it into another transformer, another self-attention here, right? It starts to generate one sequence, right? And then gradually it just, one layer, second layer, and so on. And gradually I start to see the English sentence, right? Can't I do that? Well, I can do this, theoretically, but there are two major issues in this process. So do you get how I want to build my encoder and decoder? Because I have my experience says that people sometimes lose this point, right? Because many people, as I said at the very beginning, think of those attentions as the output of the translated sequence. This is not the translated sequence. It's just features, right? And do you see that? This is why I indicated at the beginning what we are doing. So I get my sequence once again. I get my sequence in German, and then I process it. I get a sequence of numbers, right? These are the features, right? Now, I have a bunch of other self-attentions here, right? I get the last output. I give the last output to the first self-attention, right? And I process in multiple layers. Then the output that I see after doing multiple layers at this side, I want to see the tokens in English, right? Everybody sees that? Now, yes?
The input size is T.
Yes.
Capital T, and if you do that, you also get
T?
T,
Right.
But they're not like same size.
Yeah, but you can just put a remaining one empty, right?
Okay.
Yeah. But you are saying a valid point in terms of sequentiality of the whole process. This is the issue that I want to talk about. Yeah. But if you're only concerned about having like a sequence of different size, right? It's not a problem. So usually you don't build your your self-attention to be of exactly the size of the sentence you have, right? What is the limit of the input for ChatGPT? How many tokens? Giant, right? That is the size that you consider as the input, right? So you can have a sentence of size, I don't know, 50,000 tokens, right? Now you give it just 10 tokens, right? Doesn't matter. It can simply ignore remaining ones, right? There is nothing. Of course, any transformer has a limit for the input, right? It cannot process more than a length, right? But that's okay, right? And if that 50,000 is large enough, then a sentence of 10 tokens would never be translated into a sentence more than 50,000, right? So you still are fine in that sense, right? But the issue that you might have in mind is that about the sequential generation, which is a very valid one, and this is the last piece we need to understand. But everybody got the idea of what I want to do, right? I just stack a bunch of self-attentions here. I process my sequence into a sequence, those sequences, that very output sequence is the best features I have. I get that sequence, again process it with a bunch of self-attentions at this side, right? And then I get at the output a sequence which is hopefully the translation I want, right? Now, this is the idea. So I get my X. This guy, this is indeed a long sequence, right? I'm just showing it compactly in this form. This guy goes inside a multi-headed self-attention module, right? It gives me one sequence, right? And I process it over and over and over, n different times, right? Once I have this one, I get this one, I put it into another self-attention, right, at this side. And again, I process it maybe this time m times, right, a different depth, right? And then I get a sequence. Hopefully that sequence is the translation. Can I do that? I mean, I can try it, right? But there are going to be a bunch of obvious issues here. The two key issues that they started to see was, the first one was at the encoding part. When you are doing encoding, you need to know the sequential order, right? Just think about a text in any language, right? Two words, when they are next to each other, right? The order matters, right? If you change the order, then the sentence could get wrong, right? Grammatically. Or the meaning could even change, right? So you cannot simply ignore the time order in your input, right? But right now, the self-attention is not doing this, right? The only thing that is going to change is that the corresponding output are going to flip, right? But if you compute any context out of these numbers, right, this is the same thing, right? Like if you have a self-attention, the whole sequences go in. The sequence goes in like I am happy, right? The output that you see are a bunch of numbers, 1, 2, 3, right? And then I say I happy am, it's going to be 1, 3, 2, right? Nothing going to change. Now, if I want to just pass to my decoder 1, 2, 3 or 1, 3, 2, and the decoder itself also has no idea what is the order, right? Then the decoder also is just generating some sequence which is meaningless, right? Right? Yes?
The output of the softmax doesn't depend on the relative positions of the filters?
No, you can check it, actually. Because you are just generating in parallel keys and queries, right? When you change them, all of those inner products are going to change, right? Exactly the same flip, right? And then because of that, the output of the softmax, as long as you are generating it with the same temperature, meaning that the same coefficient at the exponent, then you're going to have same set of weights just flipped. Yeah. You actually can do very simple example. We have it in the, we have it in the generative model lecture notes where we discuss the context generation. And there's one simple example. You just change like the order of the sequence, and then everything is kept the same. Then you can show that the output that you get at the very output of your self-attention is going to be exact flip, right? Of course, you have a bunch of nonlinearity in practice which might change the thing, but it's not too much sophisticated that somehow give any sort of hint to your model that there is anything about the order, right? So you see that there is a challenge here, right? Your architecture is very efficient in parallel processing, but the issue is that it's unable to capture the time order, right? This is one thing that we have. The other thing is in decoding, right? Say I have processed everything, right? And I got this sequence, which is a bunch of numbers, right? Explaining I am happy, right? And I want to translate it into another language, right? That language cannot, I mean, of course it can look at the whole sentence and say like where I should put things, right? But when it wants to generate, it cannot generate like every single word based on the next word, right? The thing that is happening, I mean, if you are thinking simply, maybe translation is not the best example, but maybe think about language model itself. If you are trying to decode, and in decoding you just want to generate the next word, right? Like what we did at the beginning of the chapter with RNN. Every single time that I want to generate the next word, I cannot rely on the next words which do not exist, right? I can only talk based on what I have said up to this point, right? That was the idea. So I say, The first word is just randomly I, but the next word is now a bit limited, right? It's not going to be is. It should be am or some verb conjugated properly, right? I am. Then after that, probably I need adjective or noun, right? So you're going to limit more and more, right? Very, then it's going to be definitely an adjective, right? And then it's again limited in terms of generate. So every single time that I generate, I need to look at past time, right? I cannot look at the future, right? Because this is not a causal way of generating things, especially if you're thinking about text generation, right? So that is also an issue, because every time if I get the whole thing and give it into my decoder, then this decoder, every single guy inside the sentence is going to be generated by everybody, right? But what if I don't want that, right? Everybody sees what I'm doing? Yes? If I am generating the whole sequence by self-attention, right? I get the whole processed version at the output, right? And I give it here, right? Now, if I have the whole sentence, it's okay. I get this guy and I get the translation. That's fine, right? But think about this. I'm talking to my machine, right? I am, then what does my machine do, right? Maybe it processes that, right? I am, it just put anything else empty, and it processes it, it gets a sequence, right? And then this sequence goes there, right? Now, if my decoder is relying on the fact that I need to see towards the very end of the sentence to be able to write down the sentence at the output, right? Then it's not going to work, right? Whereas I need to have a mechanism that I tell it that, okay, or a kind of mechanism at the decoder that when I say I am, is able to generate that output, corresponding output, and when I complete my sentence, very, then it can just add this to the context that it had before, right? So you need a kind of sequential decoding as well, right? Where the decoder is only relying on the previous thing. This kind of sequential encoding and decoding was coming by nature inside RNN. Because in RNN, the processing was sequential, right? Every single time you had to look at the memory before, right? And this way you were somehow sequentially processing things. If you change stuff, then the memory changes completely. So you have the encoding sequential, and you have the decoding sequential, because the first word is generated, new memory computed, the next word is generated out of that, right? But here we are not doing this. This could limit the applicability of this architecture, right? And these were the two issues people tried to address in the original paper to complete the whole architecture. For the first one, what we do is called positional encoding. Very simple idea. For the second one, again, a very simple idea, is masked decoding. Now, in simple words, positional encoding is that in addition to give the token every time, you also give a coded version of time, right? You say this is token 1, and it's happening at time 1, right? This token is am, a representation of am, word am, or very, and then it's happening at position 2, right? Then when token very happens at position 2, it's going to be different from the token very happening at position 10, right? Because token very at position 10 is going to be labeled with time 10, right? It's a different thing. So this is the positional encoding that you do. And for mass decoding, whenever you want to generate something at time t, you just ignore anything afterwards, right? So when you are computing that alpha, the attention weights, you just put them 0 for future time, right? And by doing that, none of the values of the future time is going to show up in your computation. And this means that your decoder is generating sequentially, okay? Now, you got the idea, right? So I'm going to explain it one by one. So positional encoding, as I said, you just add the time index here, right? So you say this token is I, right? And it's happening at 1, right? Am happening at 2, very happening at 3, and so on, right? So you add the time index as well. So how can I add this time index? Well, maybe I am showing I by an embedding, right? For example, I tokenize, right? And then this I is not really I. It's a vector, right? A vector of numbers. For example, a one-hot vector, right? Then I can add one extra index, and that extra index is going to be time, right? So if this guy is of size dimension 100, then these guys together are 101, right? Yes? Yes, it's going to fit into that one. But I'm going to say, I mean, one dimension is going to do nothing. And you need to do it much more efficient. Yeah, I'm just giving a raw idea, right? Right. So if this is of size 100, this whole thing together is 101. Then this 101 is one token or one embedding of token of size 100, bunch of numbers, right? And there's one last entry telling you what is the time, right? So this way, when I happens here, is going to be represented different from I happening at time 2, right? Everybody's clear? And this is the way that you somehow inform your architecture, your self-attention, that what is the order, right? Because you give time index for every single token, right? So what you would do, you would get your original token along with the time, and you consider it a new token, right? So the new token is somehow capturing the time as well, right? But obviously, this guy would not be very efficient. Do you have any idea why? I mean, it's not necessarily easy to see it, but if you see it, that's great. And you don't need, yes, go ahead. Yeah, but that's okay, because my input size, that capital T, is fixed, right? It's not about the idea. The idea is okay. I mean, showing the time with only one number, is it a good idea or not? Yeah.
Can you exceed the character limit? I mean, if you have very long sequences?
No, you cannot. In transformers, you cannot. But that limit is very large. It's like 50,000 something nowadays, right? So that's not a problem. Now, I'm talking computationally. Do you think it's a good idea that if I want to inform my architecture about time, I simply put the time as well? Like I start from a token of size 100 and then I make it 101? It's not a good idea. The reason is simply because you don't necessarily see it. I mean, gradually, if you work with this architecture, you start to see it. But the key point here is that this one extra dimension is doing nothing, right? A vector of size 100 and 101 are not that different, correct? Probably if you want to do that, you want 100 your token, right? Maybe 50 extra components for time, right? So it's not the best idea to copy T itself because it's going to get somehow lost in the computations, right? Yeah, this is what we say we need to have a kind of rich embedding of time. And we always do it in generative AI. For example, if you're conditioning something. Because if you just simply tell your neural network, yeah, this is the whole token, and it's happening at time 1. Yeah? It's going to forget it, right? 1 is nothing. Like, it's going to have a 1 weight. And you know that all of those weights are just, trained, and some of them get to 0, and, But you need to say, like, this is the whole token, is happening at time 1, 1, 1, 1, 1, 1. Maybe you need to do that way, right? You need to keep saying it, right? This is something, as I said, computationally important. Theoretically, it should work, but this is not going to work in practice simply because of the computation. And what you're doing instead, so this is just the thing I told you. This is going to be sequential. Now we're going to have time permutation is going to change the input. But what you're going to do, you're going to just use positional encoding, right? So for every single time, you're going to compute one vector of time, right? That pt is just representing time t, right? So maybe it's a kind of weird vector, which is for time 1. Another weird vector for time 2, another weird vector for time 3, and so on, right? The key idea about that vector is that this is very large, right? And then this is not going to get missed by your neural network anymore, right? When it's doing the computation, half of the computation it's doing is about the time, right? And it's going to keep that in mind very well, that this is time 1, right? So This is why we call it positional encoding. So we get the time and we encode it into a vector. Now, what do you suggest to do for this p? How do I compute that? You can leave them to learn, right? You can say I have p1 to p capital T. This is the maximum number of time indices you could have, right? Every single of them is a vector of size, I don't know, 50, right? And then these are learnable, right? So when you are just training your model, you also compute the gradient with respect to these ones, and then you update them. At some point, they're going to get perfect, right? This is one way that you can do it. Another way that people found out is that you actually can get one weird kind of signal, like, for example, a sinusoid, right, in time t, and then you sample from it as long as you want. Like you want a vector of size 50, you just sample it, right? And then you change the frequency with time. If you want to just represent time 1, you get sinusoid with frequency 1. If you want to represent a sequence of size 2, a sinusoid with frequency 2, and so on, right? This is another way. You can check it up in the literature, but that is not really important. You have it already implemented in most libraries. Time positional encoding, going to get the time, the index in the input, and gives you back one vector. And how you get that vector, that is your choice, right? But that must be a vector. A single time is going to do nothing, right? It's going to get simply lost. Everybody's clear? Doing what? Sorry. Okay. Oh, I see. You mean that you take it in time. You can do that, but you don't do it usually in transformers. Like if you do a very good positional encoding here, then they are going to capture that. Yes, inside that. But the idea that you say is, for instance, important in diffusion models. So in diffusion models, we do the time encoding by skip connection, because it's very important in that sense that every single time that you are trying to diffuse, you do know which step of diffusion you are in. So, I mean, I don't expect that you see it exactly because you need to know the details. But just I wanted to say that this idea that you had is a valid idea, and in some applications we do it as well. So it's going to put more emphasis on time, right? Yeah, every single layer you say time 1, time 1, time 1, right? This is a good idea. But here you don't need it, because that kind of input encoding is fine enough. Yeah. Yes.
Why do you make the position some weird, multiple ones?
Yes, but multiple ones is probably, again, not a very good. I mean, you can do it. It's still going to work, but probably this is not the best choice that you could have, because usually those values inside the vector, right? You don't want to have 1 and 50,000 as well, right? Correct? As the value of one integer, one entry. Like size in the transformer here is 1, 2, here is 50,000, right? And if I want to do your idea, then this vector is going to be 50,000, 50,000, 50,000, right? And this one is 1, 1, 1, 1, 1, right? What do you mean?
Because you said a single one is going to loss. So
yeah, you do. I get your point, yeah. But here, then it's going to be 50, a vector of length 50, everybody is 1, right? What about this one? It's a vector of size 50, everybody's t, right? No, everybody inside it is t. Value t, right? Yeah. 50 entries, every entry is t, right? And I tell you t is 50,000. So variance is huge, right? This is not a good idea. Probably what you want to do, you want to have 50,000 different vectors being roughly orthogonal, right? And then each of them is telling one time, right? You can do that. You can do it by sinusoids, of course, because sinusoids with different frequencies are orthogonal to each other, right? This is one way you can do it. Or you can just simply leave it to learn, right? You say there are 50,000 different vectors. I don't know what they are. I just leave them as learnable parameters. When I'm training, I also understand what they are, right? This is another way. Questions? No question? Okay, that was about encoding. The next part is about decoding. So as I told you, what you want to do when you are decoding now at this stage, you're decoding. You're not encoding anymore. What you want to do, you want to get your input. Maybe it was not the best idea to put it as x1 to xt because you still think about the input to the encoder. But this guy is input to the decoder now, right? So sorry for that. x1 to xt is not the original German sentence, right? This is the processed version which is finished at the encoding and now goes to the decoder, right? And now this guy that comes in the decoder, what you want to do, you want to generate your every single time output depending on the previous times, right? So you don't want to generate your first token thinking about the future, right? Everybody's clear? This is what you want to do because you want to keep this sequential generation at the output as well. How you can do this? Simply just kill whatever attention you have for the future time, right? Because every single time at the output, you're computing the output in this form, right? You get at that time your attention with everybody, right? And then you multiply those attention weights to their value, right? But then you would say, I don't want to have any impact from the future, guys, right? So I'm going to set the future attentions to 0, right? So this is the way that we do it. So anything after my own time, so any j that is t plus 1 forward, I'm going to replace that attention to be 0, right? And this is a kind of well-known idea. We call it masked decoding, right? When you are decoding, you're just simply sampling based on whatever you had up to this point, not in future. Okay? Yes?
Is there never a relationship where a word depends on the network?
It depends, but the key point here is that when you have done right encoding, right, anything that you need to know right now about future to translate correctly is somehow embedded inside your first attention, right? So this is the whole idea of temporal correlation extraction, right? So you don't really need that. But yeah, let me just finish this one first, and I get back to that point again. So, so I can simply ignore whatever I have in the future. This means that I'm going to compute my value in this form, my attention value in this form, with everybody after my time being 0, or I can simply say I'm computing based on my attention to that point, right? So I get whatever attention weights I had up to this point. I ignore the future, right? And I multiply that with the values, right? This way, the output that I compute at time t only depends on h1, h2, h3 to ht, right? And anything in future is simply set to 0, right? And this means that everything you compute at time t is depending on anything you had up to this point, right? Everybody's clear? So this is the idea of mass decoding. Now, one point following the question your friend asked, there is actually a bit of more context into doing this when you do mass decoding. Now, I'm going to give you just as a hint. If you're interested, you can check it out. But if you take like course on statistical learning or data generation, like we discussed it in generative AI course in the beginning part, is a good part of the course. This is because we are doing what we call it autoregressive generation. And what is autoregressive generation? Like every single time I am generating based on whatever I have seen before. Why I do that? Because of Bayes' chain rule. I want to know the joint distribution of the whole tokens, the distribution of the chance of first token, probability of the second token given previous one, probability of the third token given the two previous ones. You multiply them together, right? Chain rule says this is the joint distribution, right? But if you do not respect this chain rule, then every single time you're generating probability of one token given everybody else. And when you multiply them, you are not ending up with the joint distribution, right? I do not expect you to see it immediately. I just want to give you this context that there is a theoretical reason behind it. That when you are doing autoregressive generation, like this is what we do in language model, mass decoding is statistically needed. Like it's going to make the whole process wrong mathematically, right? And because of that, mass decoding is not simply a one idea. It's really needed, okay? Everybody's cool? But for the level that we have right now is just simply you want to keep this sequential order at the decoding as well. Okay, now, if you do that thing at the encoder, mass decoding at the decoder, then you are going to end up with the transformer. So the transformer is actually one encoding-decoding architecture. It's purely based on self-attention. And then you do your encoding by multiple self-attentions. You do your decoding by multiple self-attentions. And then this is going to be a transformer which is able to transform any sequence into any other sequence. Now, the best practice that you can use it, or the most natural practice, is for text processing, which is the reason that it started to be the main or the core model for language models, right? But gradually it started to get into other domains as well. For visual, well, you get your data, you process it into a sequence by just making into patches. Every single patch of your image is one entry inside your sequence, right? Then you process it using self-attention. You get whatever you get at the output, and then you process that output to get what you want, right? And it is now enabling you to transform many kind of modalities in data, like visual data, into the other modalities, right? Text, all right? So you start from image, you use a vision transformer, you patch it, and then you'll treat it as a sequence, you process it, you get your output, right? That output is a giant sequence, is somehow telling you the temporal connection between different patches of your image, right? You pass it to a decoder with masked decoding, right? Self-attention with masked decoding. Then you start to generate tokens, right? Sentences. And then you get that image, you caption it, right? You get your text, you process it, you get your output of the attention mechanism, right? You give this one into a decoder which is able to look at a sequence and generate a sequence of patches, right? And then you're going to get the text, process it, then the processed version is going to be given into the decoder. The decoder is able to generate patches of images, right? Give me image of a cat, first part, second part, and so on. It completes the image of the cat, right? So it's very flexible now, right? And since you are doing the computation very efficiently, it's cheap to just make it deep. And this is why AI got a kind of super boost, right? Because you now can do crazy things that at some point of time people knew they could do it, or they believed they could do it, but they didn't know how to implement it in practice. This is making it feasible, right? Easy to examine new things. Now, this is the architecture they had in the original paper. So here you have encoding. The encoding is just doing multi-head attention. It is doing, this part is just one extra output layer. So I told you one nonlinear layer, one activation, but in the original proposal they also added a bunch of weights before activating, just to increase the complexity of the layer. Now, what you are doing here, first of all, you get your positional encoding, right? So you have your input, you do the positional encoding here to just encode the time into your sequence, and after that you start doing multi-head attention, and so on. You do it for n times. The output is coming out, right? You ignore right now this guy, okay? Don't think about this one. The thing that you do, you start from here, okay? And you generate your output, right? Everybody's clear? So this is what you're doing. You're doing encoding. You get your sequence here. Then you give it here to your transformer at the output. This transformer at the output, again, does multiple layers of attention. And at the very output, every single time, so that very last attention that you get, every single of them, you pass it through one softmax. You get one distribution. You sample the token, right? Another softmax. You get the distribution, you sample the token, and so on. So it generates the token. Now, the thing that you see here is the masked decoding version, which says that when you get your first output, random output, right, you look at that one, because if this model is simply talking, right, it wants to just build a sentence based on what it already has said, right? and every time that it generates some output, then you're going to get that output back, and then you do mass decoding here, right? So you get your output, like your last sentence, right? Or your last set of tokens. You give it back. And again, you do positional encoding here because, again, this is a sequence. You need to tell your transformer what is the order there, your self-attention. And then after that, you just do mass decoding. Like you ignore anything before, and you keep on generating, right? Now, the architecture sounds a bit complicated, but if you break it down exactly the way that we did, every single component, you really know what it is. This one is the mass decoding, as I told you. This guy is the encoder. Here we have a bunch of skip connections, as I told you, because basically they checked this is going to make the training more efficient. It's exactly the same reason we did it in Chapter 5. And then here you see add and norm, right? And this addition and normalization, first of all, add is the skip connection that we have, right? The thing comes, you add it up, right? And then you do normalization. So we have done batch normalization, right? This is the same idea, but they don't simply normalize with the batch average. They normalize with a layer average. This is what we call a layer normalization. Is exactly the same thing that we did before. The only difference is that when you want to normalize and you want to average whatever tensor you have, instead of averaging over the batch dimension, you average over the layer dimension. It's only different in that sense. And it's just a simple normalization. And then, yeah, the positional encoding, we had it here. And these layers that you see after the self-attention, as I told you, is just nonlinearity. Okay? Now, one thing here. If I remove this guy, okay, completely, and only I have this one, this single decoder, this is a language model. It generates the first token, okay, and then it gets the first token. It does mass decoding because it doesn't care for the future. It hasn't said anything yet, right? It only look at the previous guy, right? It generates the next token, right? You get the next token, now you have two tokens, right? Again, this guy goes in, right? And then it looks at only the first two tokens. It's mass decoding. It does not pay attention to future. It generates the third token, right? And keeps on going to complete the sentence, right? So the decoding here, even though that the process and training can be done in parallel, the decoding is still sequential, and there is nothing you can do about this, right? This is a nature of language model. This is an autoregressive model. You can do nothing about that, right? But the key point is that when you are training, you can do the computations very efficiently, right? And the training has a high order of parallel computation. Now, when you have both of them together, then this is encoding-decoding architecture, exactly what we had before, right? This encoding is just extracting context from the input you had. You say a sentence in German, is extract the context from the German sentence. It's going to feed it here, okay? And when you feed it here, in addition to that one, you have your language model, right? Every time it's going to look at the context that it has, it generates one word, right? And then again goes back. It looks at whatever it has said up to this point, looks at the context of the native sentence, and generate the next token of the translation, and keeps on going like this, right? Everybody's clear? Questions? No question? Okay, so if you got no question, you might look at the transformer, you think it is too much challenging, but it's not really. I mean, first of all, the challenge is really worth it. And secondly, it's hugely helping in terms of the quality of the training and also the computation. So it's a huge gain in terms of parallel computations. Long-term connections, crazy, right? Nowadays, like you give a text to ChatGPT, right? A giant PDF file. And it can find out the thing that you want, right? It can find out the typos inside that, right? So you can do that. And this is simply because of those huge attention connections, right? So every single part of your text can pay attention to everybody else. It can find out what is the mistakes, grammatical mistake, everything, right? And it can really work much efficient than human being, right? And you can simply make it deep, right? If you have a RNN, it's really hard to make it deep, right? Because you need to backpropagate through time. And backpropagating a giant architecture through time is going to be crazy, right? Definitely you're going to get trouble with training, right? But here you don't have that issue at all. So it's really worth it. Does it load a bit of more complexity in terms of like the number of parameters you need to just generate something? Yes. I mean, a transformer, a basic transformer, is more complex than a basic LSTM, right? That's obvious, but, well, the task that you are doing, language processing, is much more complicated than that, right? So it's really worth it. And since we are doing everything in parallel, we really can do it, right? And you can guess this is the main reason that nowadays all of this, microprocessor production, everything got like on the very top edge because, yeah, everybody's interested to build something more efficient, matching these architectures so that they can really process fast, right? So inside PyTorch, you do have access to transformer. You basically have, call the transformer. And it has all of the components in it, right? It has the encoder in it, multi-head attention. It had decoder in it, again, multi-head attention. You can load it. You can, for example, kill the encoder to just generate. You can kill the decoder to only process it for encoding, or you can keep both to do just a sequence-to-sequence transform. And you really, I mean, it's a very good practice if you go ahead and implement it by yourself, but you should be very careful in the sense that you cannot really go beyond the limit like with your own computer. If you can only do it if you really go on a cloud server, right? So if you have access to Compute Canada, it's a good practice to train it. So there are some dummy projects online that you can take a look. For example, you can get the tiny Shakespeare, and then out of that you can train one language model by transformer, which is going to generate letter by letter, text letter by letter, right? And then if you train a basic transformer, it's not going to give you perfect sentence, but the sentences that you see or the words that you see make sense. Or at least if they are not meaningful, they do look like an English word, right? But they are not meaningful yet, yeah? But you get the idea how giant GPT is that is able to really process it, the whole, big text at once, right? So it's good to take a look at that one. This is actually the key things you're going to study in NLP course. So if you're interested on those stuff, it's a very good idea to take NLP course. And we have it also in the generative model. So in the generative model course, we start with language models, large language model, and this is the first thing we do there, which is a study